In this problem, we'll tackle a somewhat difficult max-min optimization problem. Here, we have a cylinder inscribed inside of a sphere of fixed radius, and we want to find the maximum area of the curved portion of the cylinder. The outline of what we're going to do is exactly the same as it would be for almost every max-min problem. First off, we do something to understand the problem. In this case, since it involves shapes, we're going to draw a picture. We then want to locate relevant formulas for our problem. Inevitably, those formulas will involve more than one variable, and we want to reduce it down to a single variable. And then, for the first time in this problem, we do something that involves calculus, which is to locate the critical points. And after we have this great moment of thinking, okay, we're done, we always want to make sure to answer the question that was asked, and to make sure that the answer we give really is, in this case, a maximum, because we're trying to maximize the area. Okay, time to draw the picture. First, we need the outer sphere that has a cylinder inscribed inside of it. The question is asking us to maximize the area of the curved portion of the cylinder, and that is exactly this sort of shape, not the top and the bottom. And here's an improved version that I used a computer to help me draw. You'll notice that I've highlighted that I'm going to need the radius of the cylinder. That's just this distance right here. And I'm also going to need the height of that inscribed cylinder. The surface area we want is given by 2 pi r h, where the 2 pi r term corresponds to the circumference of the circle, and we're multiplying by h because that circle has been stretched h units in the y direction. In order to reduce our expression to a single variable, I'm going to exploit this right triangle, where one side corresponds to the height of the cylinder, another side corresponds to twice the radius of the cylinder, and the hypotenuse is twice the radius of the sphere. Since the opposite side divided by the hypotenuse is the sine of the angle, we see that the height of the cylinder is twice the radius of the sphere times sine of theta. Similarly, the adjacent side over the hypotenuse is cosine, and so the radius of the cylinder is just the radius of the sphere times cosine of the angle. And so we get the surface area is 2 pi times r cosine theta times 2r sine theta, simply by substituting those two formulas in, and we've reduced our problem to one that involves only the variable theta. Rearranging terms, we get that the surface area is 4 pi r squared times cosine theta sine theta. And we want to remember that the 4 pi r squared is a constant term. And so to find the derivative, we simply need to copy the constant term along and then use the product rule on cosine theta times sine theta. The derivative of cosine is a negative sine. The derivative of sine is cosine. And so we get 4 pi r squared times the quantity, cosine squared theta minus sine squared theta. We have to set that equal to 0. And so we need to figure out where cosine squared equals sine squared, or said another way, where tangent squared equals 1. The only values of theta we're interested in, by the way we set up the problem, are those that are between 0 and pi halves. The only solution in that range is for theta to be pi halves, and we now have our leading candidate for where that maximum occurs. We should celebrate the fact that we figured out that theta is pi force is the critical point for finding the maximum area. But we want to make sure that we actually answer the question and not lose any points by not writing down what the maximum area is. This is an easy thing to do. We just need to plug pi force in for theta. And so we get that the surface area is 2 pi times the radius of the sphere squared once we've simplified all of those expressions. If any part of the trigonometry in this question made you pause or hesitate because you weren't quite sure exactly how I was getting these done, that's a great signal that reviewing some of your trigonometry skills would be a really helpful thing to do. And finally, we should make sure that theta equals pi 4 corresponds to a maximum. You also get the derivative equals 0 at a minimum, and every now and then your derivative can equal 0 at a moment that's neither a maximum nor a minimum. Sometimes you double check this using the second derivative test, but I think in this case the first derivative is a little bit easier. For example, over here we have the graph of sine and cosine. And we notice that when the angle is bigger than pi force, sine is bigger than cosine, which means that cosine squared minus sine squared is going to be negative. Similarly, looking at values of theta a little bit to the left of pi force, we see the derivative is going to be positive. And so we must be increasing and then decreasing, which means that we really did find a maximum value. You can also double check that you found a maximum just by looking at each and every one of the critical points. Right? The critical points occur where the derivative is 0, where the derivative doesn't exist, that case didn't happen for us, and at the natural endpoints of the problem. So I have plugged in the value 0, which is one of the endpoints, and the value pi halves, which is another endpoint. In both cases, the surface area ends up being 0. However, at the angle of pi force, we know the surface area is 2 pi r squared. That's bigger than 0, and so we know we've got a maximum.